here we try to draw, you guys drew a few graphs, and then I asked you to do a weak base being titrated by an acid. So here's what I'm going to do right now. I'm going to actually give you some information, and then I'm going to ask you guys on your own together to come up with 6 points on the graph, and I want you to graph it. So here's the base information that we're going to use the same data that we used before, and it's going to be given 100 milliliters of 0.5 molar NH3. Ka 1.8 times 10, or Kb 1.8 times 10 to the negative 5 is titrated with, so right next to at the top there, or wherever you want to, 0.100 molar HCl. Okay, so what I want you to do is I want you to draw the graph for this. Now let me tell you the 4 absolute points that you have to have on every graph that you draw. Number 1 is going to be before we add any big dog in. So just the whatever we're titrating. Number 2 is going to be the half equivalence point. Number 3 is the equivalence point. And number 4 is some point past the equivalence point. And I just realized that I'm on myself. So I'm going to put this back up to the board where we're presenting to everyone. Now, what I would like you to do here is between the initial and the half equivalence point, do another point. And between the half equivalence point and the equivalence point, do another point as well. So between the half and the equivalence as well. Now, I'm going to allow you guys to decide which points to use and how much to add. Now, your starting point, just to make it really straightforward for you. Yeah, I just realized that I wasn't doing that. Sorry, Jackson. It should be on her right now. So the starting point is always what happens before you add any big dog in. And that's just an ice problem. Can you do me a favor? On the far right-hand side of the board, can you make a graph, like an L graph? Yeah. So we can, a little bit, oh, yeah, that's perfect right there. And then we can shift the screen over. Make it a little bit longer. Because we're going to be a little more intricate on this graph. Wonderful. And can you slide my screen over just slightly so the right part of it's with the given? Okay, so here's what I want you to do, and Kayla, you're going to be kind of the organizer of this. Those are the 6 points that we have to have. Now, realize we need to know what amount of HCl we're adding in each case, because the x-axis is always milliliters of HCl added. So if you want to put down below there, milliliters of HCl added on the bottom, and then pH is going to be on the y-axis. And you're probably going to have to slide my screen just slightly over so we can see, because I only see half of the H in the NH3. Just like a smidge. Perfect. All right. So the first step is going to be just doing a regular ice problem, because that's all we have is the NH3, and you're given the Kb. Actually, you need to slide over just a little bit more so I can see the ice. Did you write ICE? I can't see. And do me a favor, those of you who are watching, which I see a lot of you are just watching this here, I want you to do this graph, but try and compete with Kayla as fast as she's doing it, so that you guys are trying to take these steps on your own. So pretend that that was the problem you were given, and you actually have to write this on your own, and you have to do it on your own. The question would be like this: given that information on the top, sketch the titration curve for this. Is there any? I know I'm asking you a bunch here. Can you tilt the screen down a little bit here because I can't see what you're doing on the bottom. A little bit higher up.
There's like literally no possible way I can get the entire board.
Okay. So then it's just more important to do whatever you're doing at the current moment. So a little bit. Okay. So our initial pH is 11.48. Are we all okay with that? So let's go over to our graph, and let me help you with the graph. You're gonna have to probably shift the camera again because I can't see what you're doing. Let's make a 0 through 14. So maybe go halfway up the line, halfway up the pH line, make a 7, and then put little individual hash marks all the way up to 14.
I'm gonna be restarting my computer, but like I can still hear you on the other one because it's just being really bad right now. My computer.
Is 14 the very top one, Kayla, or is it one? Can you write 14 on the top just so we have a frame of reference? Okay. So this case here is 11 point. What was it? What did you say it was 11 point? Okay. So now watch. You guys have to decide which points you're going to use, and remember, from here on out, now we're adding big dog. So can you write the big dog equation somewhere on the board? Maybe the top of the board right there. Can I make this a lot easier for you? Get rid of that CL. Because HCl is really H plus and Cl minus, and we don't care what the Cl minus is doing. So that's the big dog equation, agree? And let's write ICF next to it. Now, the big dog always has to be done in millimoles. So how many millimoles do we have of the NH3?
Oh, yeah. 0.1. Wow, I'm sorry.
So 50 millimoles. In case you're wondering here, let me just remind you, molarity is equal to moles over volume, right? Molarity times volume equals moles. Let's do this on the, can you slide the screen over to the left-hand side again, and underneath the focus sign?
Oh.
Underneath the focus sign is already, it should be something written there, right?
Left.
The other direction. Okay, so over there, do you guys see at the bottom it says molarity equals N over V, and then MV equals N, and then yeah, those are the ones you're going to use. So now get back. Now it's tilted all weird. Okay, so the question is, how much H plus are we going to add in this case? And don't we want to have some spot between 0 added and the half equivalence point? How many millimoles should that be?
25 would be.
You guys can all jump in here.
15.
15 is a good amount. So why don't we put 15 millimoles for the H plus?
Wait, no, moles or milliliters? I guess.
So if you want to do like B is 15 milliliters, 15 millimoles, but isn't 50 millimoles, how many milliliters is that? It's 150 milliliters. Very good. That's important because we need that to draw a graph. We start with 0 of that. And then we're subtracting 15 from everything. And you're going to plot it out. James, did you really just send me an email instead of just dropping it in the Google Drive? Oh, man.
It didn't work at all. We tried.
What do you mean?
Like Lauren knew what she was doing actually, but it just didn't work. Like it didn't show up to be able to drop it in. So.
Ugh. Okay. I really want all of you guys doing this simultaneously with her, pretending that you were doing this on an actual AP question.
I'll calculate it.
Oh no, you gotta do KA.
Yeah, it's 5 point.
All right, thank you, Jackson, for helping out. So the next question we have here is how far apart do we want each of the values we're adding in? And the problem is if we're adding to get to the equivalence point, will you guys acknowledge that we're going to have to add 500 milliliters of the H plus? So if we put the 100 really far over, we're going to end up with a really, really stretched graph. So I would suggest maybe making the 100 half that distance, or maybe a third of that distance.
Okay. So you know we do 150.
So like maybe maybe about an inch from the line. So put your finger along the x-axis. Yeah, right there. That's perfect. So then you're going to put that at the 100 and then evenly do 200, 300, 400, 500, all the way up to 600 or 700.
Do I still write 100?
I'm sorry?
We did 150, not 100.
I understand that. But your graph, it's going to be awkward if you do 150, 300, whatever. So we're going to do 100, 200, 300, 400, 500, 600. And that's typically what you're going to want to do on your overall graph because we can kind of guesstimate where the 150 is going to be. And do you see if we put the 100 mark really far over on the x-axis, we're going to end up with a completely flattened out graph, which we really don't want to do. Okay. Now, remember how we did the weak acid last class period and how it shot up? Well, the same thing happens here with the weak base. It shoots down first. So we've gotten a point in between the 0 point and the half equivalence point. Let's go to the half equivalence point now. And there's something that's always true at the half equivalence point. What is it? Someone say it.
pH is equal to
Yeah, pH is equal to pKa at the half equivalence point. So can you do me a favor, Kayla? You can just write for the half equivalence point. You don't have to do any math or anything. All you have to do is say pH is equal to pKa at the half equivalence point. That is enough for a grader to understand that you know what you're talking about. So that means that we can just take the now. If you look over under the focus sign, didn't they start us off in this problem? Did I give you the KB? Yeah, I did. So they gave you the KB. Now there is a way. I mean, we did use the Henderson-Hasselbalch equation. I didn't verify, but I'm assuming you guys converted to Ka. Yeah. You can use that same Ka right here.
yeah, it's
Hey, Pichon.
Did you draw that line all the way over at the 500 mark?
Yeah.
That should be the half equivalence point. Should be at half the amount. So that's actually another big thing here. So wouldn't the half equivalence point happen at 25 millimoles?
yeah.
Can you go up above to the? Do me a favor. Can you go up above to the big dog equation and see where it says 15 millimoles? Can you change that to 25 millimoles? No, I understand that, but just do that for a second. Just change that to 25. Now, you don't need to have the 25 millimoles to solve anything in this problem. However, you do need to know what the volume is of 25 millimoles. So if you ever want to figure out what the volume is of 25 millimoles, you can take the 25 millimoles and the molarity, and can't you divide to get to the milliliters? Okay, I'll let you guys decide what point you want to choose between the half equivalence point and the equivalence point. You guys make that determination. Where are you heading? Can you add on the list? Can you add the screen cleaner, Mimor? And también the salt and vinegar.
Yeah, 350.
Well, that's true.
Wait, isn't this single one 250? 25?
Hey, Pichon. Ball. Hey, Harrison. ¿Qué tienes ahí?
He really looks like it.
Oh, a checkbook box. That's the most exciting toy of them all.
He does.
A really cute son.
Are you doing any
You're training him early, Zion, with the soccer ball.
Yeah, honestly.
Talking to you.
Why do you have ideas?
What did you guys decide to do for the 35 millimoles?
0.03. 0.077. 0.0775.
It doesn't make sense. It says he's asking a question, but it's a statement. It's fake.
Is she coming with you or no? Is he coming with you?
Eight, 8.89.
8.8 what?
9.
Oh, so good. Yeah. I love that. But I mean, I guess you. Yeah. It's big. I don't know. Why should I know? Like,
Okay, so now the next 2 points we're going to do are going to be the equivalence point and then some point past the equivalence point.
Hey, someone turn him up. Turn him up, guys.
okay, so now it's 500.
And hopefully you're getting the hang here. If you know the millimoles and you know the concentration, you can know what the volume is that you're adding as well. So right now, don't we have only the conjugate acid that's left over? And if we're trying to figure out what to do, we always just throw it into water and we're going to write an equilibrium. Now, why can't we use the Henderson-Hasselbalch equation here?
We don't have.
Yeah, we don't have any of the conjugate, right? All we have is the conjugate acid. We don't have any of the conjugate base.
We do? What is it? No, that's the figure of NH2. That's That's its conjugate acid base. Oh, it's just all the same.
Oh, sorry. I think it's 6.7.
Can you Mom or Audra?
5.17.
Okay. And we're going to choose one more point past there. You can decide wherever you want to do it.
I'd say we do a nice 650.
Ah, thought you were going to go on the line, but you zagged when I thought you were going to zig. Well done.
What? What do we do? Why?
I didn't do anything.
Is he just sad because you moved away from him? Diane, are you sad? I can understand that. Separation anxiety is a terrible thing.
I don't like this. 0.02.
You know, like what?
Oh no, no promising, Zion. Anything but that.
Sorry.
Trying to promise you what?
1.70.
Zion's way of threatening people is he says that he promises as opposed to.
Oh.
If you read the chat.
I got. No, I read the chat. I didn't get that promises.
Okay.
I forgot that.
Oh, I like it. That's a great graph. Okay. So let's analyze these points of the graph, and what I'm going to do is I'm going to again pretend that I'm an AP question. I'm going to ask you to label the points of the graph, label all the species at each of those points, and show me where the main buffering region is.
Aren't you?
So at the beginning, when we only have, I don't know what you're writing there because I can't really read it. At the beginning, when we only have, it's still blurry, but just tell me, when we only have NH3 at the beginning?
Do we not have NH4 plus?
None.
It's like in the middle.
Remember, because we're titrating at the very beginning, at the starting point, we don't have any conjugate base at all or conjugate acid at all.
We have water.
True. And sometimes, and that's actually a good point. Sometimes what they can do is they'll ask you what are the species, and if you wanted to include water in there, you can include water as well.
I mean, wouldn't water give NH3 a thing to make NH4 plus? NH plus?
Yeah, but this is NH3 by itself sitting there.
Meaning no HCl?
Now, let's do it at the half equivalence point. What two things are going to have at the half equivalence point?
So only reactants.
Water.
At the half equivalence point?
Let's not worry about water right now. We're asking what are the major species here. So at that second point, we're going to have NH3 and we're going to have NH4 plus. At the half equivalence point, we're going to have the same amount of NH3 as NH4 plus. Can you write NH3 plus equal to NH4 plus? And then the previous point, wouldn't it be NH3 is greater than NH4 plus?
Wait, hold on.
HCl goes into H plus, which then makes.
I'm having a hard time hearing you guys.
Well, at the equivalence point, if I have the same amount, doesn't it become zero? At the half equivalence point, it's the same.
Okay, how about that at the equivalence point? Just jump all the way down to the equivalence point. What do you have at the equivalence point?
What about the one after that?
Oh, never mind.
Just have it.
That's what I was.
Yeah, only NH4 plus because remember at the and
Oh, no.
predominantly just the H. You're just gonna have H plus as well. H plus was gonna dominate that. No, you're right. NH4 plus is there.
Explain
You're also gonna have H plus.
Can you explain this?
Like, look at the
And NH4 plus.
last equation right there.
So you have NH4 plus still. You also have H plus. So put both of them in there. NH4 plus and H plus.
Okay, can you explain why for all of
Yeah. Let's go back to the original equation you just did. We'll go back. Jax, can you slide over?
Yeah, Jackson.
Okay. Which is the one where you did at the equivalence point? Where's the math you did at the equivalence point? Did you erase it? Okay. So when you're past the equivalence point, so let's do this. Up above, you put 65, right? So let's look at the math of above. Put your finger on the E underneath the big dog. Or F, sorry, F underneath the big dog, okay? Slide over. When we're done, don't we still have 15 millimoles of the H plus and 50 millimoles of the NH4 plus? So that's why we have to write both of those things past the equivalence point because both those things still exist. I'm just waiting for do you have a follow-up question? So when we're looking at the graph and we're trying to figure out what things exist at each place, at the equivalence point, all we had was the NH4 plus. But when we have leftover H plus, we have to actually include that because the leftover H plus isn't that what determines our pH. So in that case, then we have 15 millimoles of H plus and 50 millimoles of NH4 plus. That's at the last point you drew on the graph. That's why we have to write both of them in there. Okay, go back to the graph again. And will you show me where the main buffering region is? That's the main buffering region, agree? Where's the best buffering region? Right at the half equivalence point. Now, I want to point out something to you here, and this is a true that you can always acknowledge. Can you put your finger on the equivalence point? Okay. Is that pH above or below 7? Below 7, right? Now, watch. Every time, and this is a general statement that you guys need to be aware of and need to be able to understand. Every time that you have a weak base being titrated, at the equivalence point, all you're going to have left over is the weak acid. That weak acid will form an acidic solution, which means the pH will be lower than 7. So without even looking at a graph, you should always know that the pH of a weak base being titrated will always be below 7 because at the equivalence point, all you have is weak acid left over, and that weak acid will produce acidic solution. Flip it in your mind. Let's pretend that we were titrating a weak acid. At the equivalence point, we use up all the weak acid, and all we have left is the weak base. That weak base will then produce a basic solution in water, which is why the pH will be above 7 when you're dealing with the equivalence point of a weak acid being titrated. The only time, and this is where they love to get you on these here, the only time that the pH is equal to 7 at the equivalence point is when you have a strong acid and you have a strong base. Can I get a thumbs up if that makes sense? Now, you did a whole section on, or you did a whole outline on indicators. Tell me what the best indicator would be for this particular titration. You might have to flip in your textbook to find it. What indicator would be the best, do you think?
76 at our equivalence point, right? You wanna write that down?
So let me point out something to you here. Maybe you've highlighted, maybe you haven't. But on page 745, which is 15.5, it says this: when we choose an indicator for a titration, we want the indicator endpoint where the color change. Oh, by the way, I did not make this really clear. So the equivalence point or the titration point, that's where we have our stoichiometric point. All those are when the whatever we're titrating is completely used up. The end point is different. The end point is when our indicator changes color. Bear with me. So what they tell us here is this: we want to choose an indicator where the titration equivalence point to be as close as possible. The typical rule is this: take the pKa of the indicator and -1, and that's what we want to get as close to the pH as possible. In this case, what's the pH that we have? 5.17. So if we take our pKa of our indicator, what's the Ka of methyl red? Do we know?
I don't know.
No, it says it's pH.
Just
The
on the
midpoint
pH
looks to
thing
be.
is.
Yeah. So, but just be aware of this. Whenever we're trying to figure out the pH, we're going to want to have the pKa -1 of the indicator.
5.0 into the -6. .3. Oh.
4.30.
We could try.
That's actually a little past.
Yeah.
So I would probably try one that's a little bit closer and maybe even before.
Area chrome black tea. Wait, that's past it?
Usually we want to pick an indicator that is going to start showing around exactly where the equivalence point is, but you can always start a little bit sooner. So you could do it like instead of a pH of 5, you could do it a pH of 6.
Our equivalence point is 5.17.
Right. So 4.30 might work. But is there anything that has more of a pH closer to 5 in the center?
For a basic solution, don't you add one, not subtract one?
It's ±1. Yeah, so that would probably work. You could also probably use like methyl red. Is that what you're using right now? You could also use probably the enochrome black. And you could possibly get away with using the bromocresol green as well. Methyl red's probably a good choice. All right, any questions on this graph?
I think that the midpoint of that range would be about where we wanted, right? And that's
Yeah, and because the idea is that the graph shoots down so dramatically that a few drops will change the. Do you guys remember did you guys remember the titration we did last year, where we were doing drop, 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 and all of a sudden we put one drop and it changed completely to like a magenta color? You guys remember how that worked? That's because that's how quickly you shoot down that line. Okay, we're going to shift gears right now, and I want to point out a couple things here that I wanted to remind you of from last class period. Can you guys turn to page 670?
Everyone said
670, which is an interactive example 14.1 or 14.9, sorry.
erase.
Erase everything, yes.
What page is page 7? Karina, what's page 7?
Okay, so if you take a look at the interactive example, they give you two different acids, HCN and HNO2. Can I get a thumbs up if you're all with me on the same example?
Why are you looking at me?
Yeah, bring him in, please. Thank you. The Ka for HCN is 6.2 times 10 to the negative 10. And the Ka for HNO2 is 4.0 times 10 to the negative 4. And you're given 1 molar of HCN, and you're given 5 molar of HNO2. Okay. And they ask you, what is the pH of this mixture?
You find the pH of HNO2 because it's stronger.
Now, listen carefully if you would. This is exactly like a polyprotic acid. Whenever you have multiple Kas and they ask you for the pH, you go to whatever the Ka is that's the largest, and that's the Ka that you figure out your pH from. Now, there has to be a significant gap between the two Kas. And if you're taking a look right here, you don't get much bigger of a gap than 10 to the negative 4 versus 10 to the negative 10. That's on a factor of 10 to the 6 difference. That's 1,000,000 times bigger for one than the other. So we're going to be able to get our pH solely from the HNO2.
4.0 times 10.
You can like go and help.
I beg your pardon?
You can like go and help. If you need to go.
That's 2 times I didn't hear you. Can you say it one more time?
You can like go and help if you want.
I can.
Well, you can like go and help your kid.
Oh no, sorry. He's he's a little bit. Thank you. Go ahead. My son, we actually let him outside for the first day. He's been throwing up every day, and so you just let him outside for a few minutes, and he is not happy being brought inside right now. Okay. So he's fine.
I'm sorry.
I was like, you need help? What? All right. So just to make this really clear, anytime they give you a group of acids, a group of weak acids, a mixture, and they ask you for the pH, you're always going to go to the Ka of the acid that has the highest Ka, and you're going to solve for the pH from that alone. ¿Está bien, Harrison? Hola, mi amor. ¿Estás bien? Yeah, I got that, Colton. Thank you.
Fine. 1.3. 1.3.
Man.
Now, the X amount, 0.045, I think it's 0.045, but I can't really tell. That 0.045 we got for the H plus amount, that's way, way, way more H pluses than the HCN would produce. So, yeah, I'm not going to spend any more time with that because that's just a straight problem. Okay, I was gonna jump into acid-base strength and salts, but instead I want you to do some practice on your own right now. So I'm going to screen share and I'm going to go to the worksheet that I want you guys to work on.
Jackson, come back over here right now.
Dang. Oh.
What time is it?
I'm going to hold off on doing the polyprotic graphs, which is what we're going to cover today.
55 seconds.
Okay, this is the worksheet I want you guys to work on in class right now. I have also included the answer key on the work on the. Can everyone see this?
I'll be yours.
I can take it. I don't think he'll do it. Will he have the courage? Stop staring at me.
Were you guys able to see that? Because I still had Kayla on present. Were you able to see what I did on the screen share? Yes or no? Thumbs up or thumbs down?
Nope.
No? Okay, so watch. This is the worksheet that I want you guys to do. I'm going to present to you. Kayla, you're going to be the voice of everyone here since I can't see the screen when I'm.
Okay. Hi, there's me. I'm back with.
This is the worksheet I want you guys to do.
Oh yeah, we see it now. Is this the one that you told us to print out like 2 days ago?
Yep.
Was that a yes?
It should have been a yes. Yeah.
Right.
Either way, if you need to print it out, you can. This is going to be your homework. It's only 10 problems.
Great.
Partner up in your pods to work on this.
Right
and if you need to, you can look at the answer key as well. Just check your work.
It's like on Monday. Right. Will do. I think. Okay. Goodbye.
Also, there's 2 other things I want you to read. So your homework's going to be that, but I also want you to read on 2 different things. I want you to read on acid-base salts again. I had you do it before, but I want you to underline and read it. And then I want you to do read on the relative strengths of acids. That's in chapter 14. So those 2 things additionally.
We just never learned it. Acid-base salts and the relative strengths of acids.
Relative strengths of acids. Those are both in chapter 14. Okay, were you guys able to? You guys know where that is? In the portal. I'm going to show you real quick. I'm going to screen share again. If you're looking for it, this is you guys right here. It's under portal. It's chapter 15 worksheets, and it's the acid-base titration worksheet. And if you see right underneath it, you have the practice worksheet here, and then you have the answer key right behind it. So you might want to just print out the answer key one because it has the question as well. But I want you to all group in your pods.
Huh? Is it on the portal?
No, but I'll put that on there right now.
Great, thanks. I'm gonna go.
Okay, I'm gonna stop broadcasting. I still want you. Can you do me a favor, Kayla? Can you take your computer and just switch it around towards the classroom? And if you guys have questions in your pods as you're going through it, you can ask me. The remainder of class time right now, you're gonna be working on that worksheet.
All right, bye bye.